The following presentation is being done on Unit 2 of the APS 162 course, which essentially deals with limits. And the following question has been taken from a book called Mathematics by R.D. Sharma, and the reference is in the description below. So the following question is essentially asking us to evaluate the limit as x tends to pi by 2 of 1 minus sine x upon pi by 2 minus x squared. And before we can go ahead, it makes sense to plug in pi by 2 into this particular function and see what comes at us, so we know how much work do we need to do. So 1 minus sine x is going to give us 1 minus 1 as x tends to pi by 2, as sine pi by 2 is 1, and pi by 2 minus pi by 2 is 0. So we are given this form. The limit is in the form 0 upon 0, which is an indeterminate form. Essentially, that means that there is more work that we're going to have to do to evaluate this particular limit, and that in itself poses a problem, because the given function has two types of functions in it: a trigonometric function and a rational function, making it difficult to try and separate the individual components of this function to find the limit. So it makes sense to try and break this down and play around with this function to make it into a form that we do recognize and we can solve for the limit. One of the most important examples possibly being the limit is x tends to 0 of sine x upon x is equal to 1. That's a really important limit that we do know of. But x is going to pi by 2. However, if I use substitution, I could make a variable go to 0 and then substitute the changes within the function. So let's try that. If I have a variable, say h, as x tends to pi by 2, h needs to tend to 0. That's my aim. So h needs to be equal to x minus pi by 2, which if I rearrange, I can get x is equal to h plus pi by 2. So I substitute this into my limit, and I get 1 minus sine h plus pi by 2 upon the denominator. And I see that it automatically starts simplifying. And I'm stuck with a minus h raised to minus h squared in the denominator, which will give me an h. And the numerator is sine h plus pi by 2. Now we notice that sine h plus pi by 2, as a trigonometric identity that we've been learning since high school, sine of any angle plus pi by 2 is essentially equal to the cos of that angle. So we use a trigonometric identity to try and simplify our function a little more, giving us 1 minus cos h upon h squared. Now this has already become extremely manageable, but it's still not in a form that we can recognize or solve. So we should play around with it a little more. And also we notice that if we put h is equal to 0, we are still stuck with the indeterminate form as cos h is equal to 1. And 1 minus 1 is 0, and h squared is of course 0. So we use another trigonometric identity that essentially says that cos squared theta minus sine squared theta is equal to cos 2 theta. Now, as I mentioned earlier, the sine h upon h, the limit of that being equal to 1 as h tends to 0, is an important tool in our kit box that we can use to solve for the limit of this function. And so we should try and get everything in terms of sine. So as we resolve the identity to give us to relate sine and cos, we get 1 minus cos h is equal to 2 sine squared h by 2. This we can go ahead and plug into our function, and we see that we get a really simplified form of the earlier function, which almost seemed impossible to solve in the beginning. But we're still not quite there, because the h by 2 that's within as an angle, we need to try and make the denominator h by 2 as well. So first, possibly we could try and split sine squared h upon 2 into sine h upon 2 into sine h upon 2. They're giving us this form. We can pull the 2 out as it's a constant. Now we need h upon 2 in the denominator, which means we're going to have to multiply both the h's by 1 upon 2, which in effect is multiplying the denominator by 1 upon 4. But that means I end up changing the function. So in order to keep the function the same, I should multiply the numerator with 1 upon 4 as well. So multiplying the numerator and denominator by 1 upon 4, we're going to get this particular result. And on simplifying it, we know that this is going to go to 1, and this is going to go to 1 as well. And using the limit laws, we can separate this quite neatly. And this goes to 1, and this goes to 1 as well. And these cancel out to give us 1 upon 2. And that leaves us with the limit as 1 upon 2 into 1 is going to give us 1 upon 2. So we use trigonometric identities as well as a bit of substitution in order to get a limit from the original 0.0 form, which was really difficult to solve. So thank you.